Thank you, Professor Ha, for you to being a chairman for the session. And I hope you are getting useful information through the sessions that we have prepared. And let me introduce the chairman for the next session, Young-bin Park, professor of UNIST. He is currently head of Department of Mechanical Engineering at UNIST, and also a director of UNIST Composites Research Center. Ladies and gentlemen, please welcome him with a big round of applause. 여러분 박수로 모시겠습니다.
Good afternoon. Thank you for the introduction. I'm Young-bin Park, and I'm with UNIST Korea. It's my great pleasure and honor to chair the last session of the day. So in this session, we have three distinguished speakers, I believe all from Germany. Unfortunately, they are joining us online. So I'd like to introduce our first speaker, Dr. Markus BRZESKI, who is the CEO of A+ Composites. He has many distinctions, but one of the greatest achievements is developing a novel impregnation process for thermoplastic tapes. And I believe based on that technology, he founded his own company in 2015. And the title of his talk will be How Much Strength of the Fiber Can Be Transferred to the Component? Are UD tapes the future? So please join me in welcoming Dr. BRZESKI. Okay?
Yeah, thank you very much for introducing me, and good afternoon from Germany. Today I would like to give you a short introduction into this topic, which is quite complex and very interesting for us because many companies requested us how much strength can be transferred into the component. Usually there's a big gap between the single fiber strength and the strength which can be achieved in the component, even taken into account the different fiber contents. So thank you very much for this opportunity. Yeah, so we are a young company founded in 2015 from the Leibniz Institute for Composite Materials in the southwest of Germany. I did my PhD at the institute, and now I would like to give you more details about the company very shortly, and then I will start with the actual presentation. So we develop thermoplastic tapes, and we develop the tapes according to the customer needs. So we select the right fiber and the right polymer and make the tape in the final width and the final thickness with the final fiber content. So we do not do slitting, for example. We make the tapes specific to the customer needs. So by now we made more than 250 different combinations, and this gives us a bright variety of experience in making thermoplastic tapes. So we already did polyethylene matrix-based tapes up to PPS or PPA material, and we did from carbon fiber different like HM fibers or high strength fibers to glass fibers, basalt, aramides, polymer fibers like Dyneema, and also metal fibers. But now I would start with the actual presentation because this is more important than to introducing the company. So we wonder why there's a big gap between the actual fiber strengths, single fiber strengths or the strengths of the data sheets, and the actual strengths which can be recalculated from the component. And from the literature, it's well known that the influence of the fiber tension is the most important one. So I will split the influence of the fiber tension in three different stages, which goes along the process chain. So we start with the actual fiber manufacturing. So when the fibers are made, they run after the processing into a sizing bath, and then they dry and we will wind up. And this is a very critical point because This leads usually to irregularities of the bobbin surface, and this leads to a different tension in the roving. As more fibers are on the yarn, as stronger is these effects, and also their crossings and the angles are very, very important. We investigate now many different carbon fibers and glass fibers, and this is really a very critical point, and there can be a lot of improvements done. Another very important point is impregnation. This is done here at A+, for example, or other thermoplastic tape manufacturers. And this is a very key point to maintain the still remaining fiber performance. So by means of a good spreading of the roving, you can improve the alignment of the fibers, and even the impregnation can help a lot, because the high viscous matrix will help to align the fibers to each other, because they draw them to align better next to each other, which is energy better situation. And by cooling, this stage can be maintained and be freezed to post-processing. From our experience, the most critical point is the post-processing, because when you now have like 90 or 80% of fiber strands left, you can lose a lot of fiber strands, which I'll show you later on. So here are very critical factors: the irregularities of the surface or crossings, two tapes, the winding angle, squeeze out, or insufficient bonding, for example. Also, the diameter of pressure vessels are very important, also wall thickness. So how we have investigated, and we found out these results. We tested all specimens on a single ply, so we make a single tape or a single tow or a single prepreg test. For thermoplastics, we reheated the material to find out how much loss will occur when you apply a tension or apply a vacuum, or if you reconsolidate the material, like for injection molding processes. And for wet winding, we wind up the material around a sheet, and we applied by this a tension, which is about 50 newtons per roving, and we cure them under vacuum, which is the standard test to investigating the strengths. And I have to point out that we monitor the loadings, not the strengths, and we monitor also the elongation to calculate the Young's modulus. So I first start with the material which we developed with Soltec together. This is material for injection molding processes, especially designed for the automotive industry. So we use a 50K roving, so a very thick one, and we impregnate them with polypropylene, which is a low-cost matrix system and is well known in the automotive industry. We achieved by this a high tensile strength of about 1,700 gigapascal by a fiber content of 50 volume%. So if we now recalculate the Young's modulus, which was about 120, and compared with the actual datasheet values, we can maintain the 100% of the Young's modulus in the tape. So this is after the impregnation step. If we now reheat the material, we lose about 13% of Young's modulus, which is quite a lot, because the fibers will go in different directions. And even if we keep in mind that the thickness increase of the deconsolidation is post-calculated, we can not achieve the original value. If we do now a tensioning, which I show you later on for the tensile forces, we can even increase the values up to 95%. And if we consolidate it again, we have about 97%, which is quite a lot. But now, if you make the organosheet, the process route will now have an additional preheating to introduce the heated organosheet into the component. And by this, you can apply a tension. But when you introduce it into the tool and stick it to the surface of the tool and holding by needles, for example, or vacuum grippers, you will lose 13% of your Young's modulus. And then the injection molding mass will consolidate everything again, but this remaining loss will still remain. So by this, it is very important to keep in mind if you use organosheets and if you preheat them, you will lose a lot of performance into the component. If you use the tape, it doesn't matter actually which tape it is. You can use a single reinforcement for a sandwich structure, for example. And if you use the tape from us, there's no reheating or preheating necessary. So you can just introduce the tape into the mold and you do not lose any tensile modulus, for example. We have two different examples. This is one which we developed together with Röchling. It's the underbody part, which we have reinforced with glass fiber polypropylene material, specially designed to increase the stiffness on the outside of the underbody part. And there we have used a special self-adhesion tape, so there was no need of tool changes necessary. Another short example is returnable transport packaging. It's a bin, and here we use the carbon fiber reinforced material, which I have shown you earlier from the Soltec fibers, and there we can decrease the deflection of the bottom part by half. Now I would like to go to the braking force investigation, and there we try to compare it with the wet winding process, which I have introduced you earlier. So if we now take the single fiber strength or the single fiber force, and if we compare now with different steps, we will find out there are tremendous decreases of braking forces. So if you have 100% set as the data sheet or as guarantees by the fiber manufacturer, you can spread it now and you can impregnate it with resin and tensioning during the wet winding process. And you can achieve a fiber volume content of about 63%, which is quite standard for this technique, I think. And if you now apply this to the plate and compact it and consolidate it by vacuum again, you will lose about 30% of your fiber braking force by this technique, which is quite a lot. If you now wind it up of a circular surface, depending on the diameter, you will even have higher losses. And if you now have a mindset, we only have investigated a single tau, if you now wind it up with several layers, this decrease will even be higher. This effect is well reported in literature. There are many papers available which give answers why this is, but one big point is the squeezing out and the irregular surface of the wet winding process. If you now go the thermoplastic route, like my speaker before, you can find out that even 91% of the braking force is still remaining in the tape, which is quite a lot. There are some differences between the fibers and the linear densities of the material, but the magnitude is quite the same. And if you now do the laser welding with different lasers, or what we have done, for example, with the hot gas torch, you can maintain most of the strengths. So if you now wind it up again, you have some effects because of the inner and outer surface length. So you can achieve about 68% of fiber strength, which is quite a lot, but I think there's still room to improvement to get a better fiber spreading and a better fiber tension. You can compare this now with the pre-mentioned treatment. So we used the thermoplastic tape. There was about 90% of braking force left. If we reheat this now with any tension applying, we decrease the braking force by about 40% or 30% from the tape, which is quite a lot. If we apply now different levels of forces to the tape for the tensioning, for example, you can improve this to about 76%. If you apply a vacuum, for example, you can even increase it several percentage more, but you cannot achieve the original level. If you compare this now with the wet winding process, where we have applied a 50 Newton pre-tension, you see that the magnitude is the same when you reheat it without applying the thermoplastic impregnation and the spreadability. So you lose about 30% of your performance, which is quite a lot. And this gives us a good idea how thermoplastics can improve and decrease weight for pressure vessels, for example. And this you can see in this slide of the comparison of different materials for hydrogen tanks. So this is a theoretical overview, but we have also done some testings on actual components, but I cannot show it now. If you compare now 3 different material combinations, so it's a carbon fiber reinforced tape and a glass fiber reinforced tape and a carbon fiber epoxy reinforced roving, which was applied by wet winding. If you investigate now the quality of the tape or of the semi-finished product, you will find out, as my speaker said before, that for thermoplastic tapes you have an excellent quality system. You can monitor the fiber tension of each tow, for example. You can have a width and thickness investigation. You can investigate the impregnation. All the process parameters are well monitored. So it's a very good and accurate process to maintain a constant high quality. For glass fibers, this is a bit more difficult because if you do not coloring them, then it's more difficult to monitor, but it's still on a very good level. And in comparison to thermoset materials, this is nearly impossible to monitor the width and the thickness and the distribution on the vessel, for example, and to find out where really which material is. If you compare now the material cost of the final vessel, it is very surprising in the first time that the material cost for carbon fiber tape variant in comparison to the wet winding variant is nearly the same level. This is due to the better use of tensile strength or the better use of the fiber than with the wet winding process. And therefore you have to apply more material to the vessel, and this leads to a higher vessel weight in comparison to a thermoplastic solution. So, and last bit is very important in these times, that you can recycle the pressure vessels if you use thermoplastic matrix materials. You can use the material, for example, for injection molding processes. So now I would like to thank our supporters. So one tape was developed together with Soltec, and other things are developed with other partners. So I just hop a bit further. So we are very thankful to DSM and to Porsche to supporting us in these areas. Now I would like to summarize my presentation. And are now tapes the future? I can give a clear yes if you develop the process right and if you have a good welding process, because the speeds are quite low at the moment. But if you can weld the tape and do not remelt the full tape, you have a very efficient process with a good quality system, which are remaining a lot of strength into the component. If you have to remelt the material, like for organosheet production or for complex shapes in injection molding processes, for example, you have to keep in mind that there are tremendous decreases of modulus and strength. And also you have to keep in mind that the tensioning of the tape and the part is very important, but it's very difficult for injection molding processes. If you compare now the thermoplastic route with the thermoset route, then it can be clearly stated that it's more easy to use the thermoset process route, which leads to a higher fiber content than for thermoplastics. But to put it in a nutshell, you can achieve a higher performance and a lower weight with the thermoplastic tape, even if the fiber content is lower. So this is due to the better spreadability by the high viscous matrix material, which leads to better alignment of the fibers during the impregnation process. So thank you very much for your attention.
Thank you, Dr. BRZESKI, for a very insightful presentation on the perspectives of the UD tapes. We have time for 1 or 2 questions from the audience. Yeah, we have 1 question from the floor. Oh, 2 questions. Okay.
Hello, hi. Yeah, as you stated in the beginning, you use a lot of fibers for your UD tapes. And I wanted to ask if you have any plan to use natural fibers for the future, or if you already have established that, or maybe had a look into it, but it wasn't that interested.
Yeah, thank you for your question. We have already made a tape out of lax fibers, for example. We have some requests to doing that, but to put it on a bigger scale, we have no high volume process running at the moment. But I think in future, especially if there's a constant quality of the fibers, it's a very interesting process, and it's good to impregnate, for example, with polypropylene.
Thank you.
Okay, we have another question from the floor.
I will speak in Korean language. Injection molding 말씀을 하셨는데요.
So you've talked about injection molding, and thank you once again for your insightful presentation. So there should be a thickness of UD tape, and when doing the injection molding, then it will melt and the tension will be lost. So do you do any research about the thickness? Because sometimes you could have the fiber straightness, sometimes you could have some crack or breakdown. So I would like to know about the thickness. Do you have any results about that kind of research?
Yes, we do. We have already made a lot of different tapes for injection molding processes. So the thickness is a very important property. If it's too thin, you have issues with the shrinkage of the original material, and you get cracks inside the tape. And if the tape is too thick, you have issues with a good impregnation of the material. So the thickness is very important point to have a good adhesion and to have no cracks inside the material.
Okay, thank you. And in the interest of time, and there are no more questions from the audience, so I know it's morning time in Germany, so thank you for your time and giving us a great presentation. So let's thank our speaker one more time. Okay, thank you very much.
Yeah. Thank you so much. Thank you very much.
Okay.